So in this video, I'll be doing a quick review for Precal honors about the trig identities, just so that way, we can be a little more prepared for our test tomorrow on these trig identities. If you remember, on Friday, she gave us a paper with a few examples, and I'll try to go over them and explain them, and maybe some tips that I kind of found while doing the homework as to how you can go about solving these problems and where to start, because I know that can be difficult. So on the first example, we have cosine x over 1 minus sine x minus 1 plus sine x over cosine x equals 0. Now the first thing I like to do for all these problems in general is I like to look at this answer on the right side and try to notice anything peculiar about it. Try to notice what it is and see how you can possibly manipulate that into that. So here they only give us 0. That doesn't really give us much information, but for the other ones that might be very helpful. So here we see the next thing I like to do is I like to look at my Pythagorean identities. So we have them right here. Try to see, if you see a square, try to look for any sine squared x or cosine squared x in here and see what you can possibly convert that might be helpful. That's the first thing I like to do. Here in our original equation, we don't have anything we can convert because we can't use the Pythagorean identities on this, or this because it's not squared, right? So I guess that only leaves us to try to combine these two terms. So we would need to find a common denominator then, right? Which is what I've done. I made cosine x times 1 minus sine x the common denominator, and then obviously multiplied this by cosine x, so that becomes cosine squared x. And then I multiplied this by whatever it doesn't have, which would be 1 minus sine x. So then it would be 1 plus sine x times 1 minus sine x, and that is a difference of squares, which leads us to have, since there's a minus here, it would become minus 1 minus sine squared x. So then we move on to the next step. Well, see, now we do have a sine squared x. This can give us options now. Now we can see, okay, now we can try to use our Pythagorean identities. The moment I see a sine squared x, cosine squared x, or anything that has a square, I like to see what Pythagorean identities we can use on it to possibly get our answer. So 1 minus sine squared x. Well, if you look at our Pythagorean identities, you can manipulate this formula, and that is actually the same thing as cosine squared x, because you move this sine squared x over, it becomes 1 minus sine squared x. We have that right there, so we can just turn that into cosine squared x. Cosine squared x minus cosine squared x is 0, and honestly, whatever is here doesn't matter because the numerator is 0, which means the whole thing will turn out to be 0, and that's how we get this. Now, if we move on to the second example, we have, let me focus the camera properly. We have 1 over sine x minus 1 minus 1 over sine x plus 1, and this equals minus 2 secant squared x. Now, let's look on this right side. We know it's dealing with secant. Secant is a version of, I think it's cosine, right? Secant is the same thing as 1 over cosine. So we probably would want to end up with cosines here somehow, even though it gives us sines. And also we would probably want to combine these terms, because see how there's a minus here? The answer doesn't have minus on this side, which means they must have combined the terms in order to get this multiplication here. So, because, yeah, as you can see, the answer doesn't have something minus something or something plus something, which means they must have subtracted these terms to get one division and then ended up with that. So I just do the same thing we did on this side, and I find a common denominator, which would be sine x minus 1 times sine x plus 1. You obviously adjust the numerators accordingly. You get, since there's a minus here, it would be sine x plus 1 minus sine x minus 1. So then now we just, I don't know, this is kind of an extra step. I don't know why I did that, but actually, no, that is vital. See, it's minus sine x, so then you kind of distribute this out, so it becomes minus sine x, and then minus times minus 1, this becomes plus 1. Then, what I did is I combined this plus 1 and plus 1 here, made it a like term. Sine x and minus sine x will cancel out, so it becomes 2 over. And I guess what I've done here is I have, I did multiply these two out, so it becomes sine squared x minus 1. Because in some scenarios, you might actually want to leave this sine x minus 1, because that might be able to cancel out with something on the top, another tip. But it can't really cancel out with anything on the top, or maybe it could. Again, there are multiple ways of going about it, but what I've done here is I just multiplied this bottom, so I got sine squared x minus 1, And if you, again, we see a squared x, instantly means we can go ahead and look at our Pythagorean identities, which is the same thing as minus cosine squared x. 2 over minus cosine squared x is the same thing as, well, since there's a minus here, the whole thing will be minus, and that's the same thing as minus 2 secant squared x. And that's it. Now let's move on to another example. We have cosine x over 1 minus sine x equals secant x plus tan x. All right. Well, you see how there's a plus in the middle? That means somehow they must have, split it up at the end in order to get to separate these two terms. And actually, eventually we do that. But looking at this answer here will kind of give you an idea, like I said before, as to what you're supposed to do. Anyway, let's just see what I've done here. So I guess what I've done, this is one of those problems where you have to rationalize the denominator. And what that means is, if you remember, there is there's a property. If this 1 minus sine x was up here and this cosine x was down here, you could do 1 over cosine x minus sine x over cosine x. But you can't do cosine x over 1 minus cosine x over sine x. That is incorrect. You cannot do that. So really, just as this is, it's hard to do anything with that. So what we're going to do is we're going to multiply it times 1 plus sine x over 1 plus sine x. You just take the the opposite of that. So it's 1 minus sine x. So we just do times 1 plus sine x. That will give us a difference of squares. And if you notice, we didn't really change this equation because 1 plus sine x over 1 plus sine x is just 1. So we do, so that's the same thing as, cosine times 1 plus sine x, and then this is the difference of squares, so it results in 1 minus sine squared x. And now we have 1 minus sine squared x. Again, I tried to convert that into cosine. Why? Because if you see there's a top term, cosine x times 1 plus sine x, this 1 minus sine squared x cannot cancel out with this 1 plus sine squared x, or sine x, clearly, because this is a square, this is not a square, this is plus, and this is minus, so that can't do anything. I turned this into a cosine because now we have a chance of cutting it with this, which might help us further develop our question. So 1 minus sine squared x, I decided to use our Pythagorean identity. Instantly looked at what we can do. We can't use these two formulas that deals with cotangent, secant, and all that other stuff. So we look at this one, and we see that 1 minus sine squared x is the same thing as cosine squared x. So I roll with that. Now I'm able to cut this cosine x, aren't I? So I can cut this cosine x, so it becomes 1 plus sine x over cosine x. And now we could try dividing it, but as you can see, the answer is in two terms with a plus in the middle, which means they probably want us to convert this into 1 over cosine x plus sine over cosine x. Now I skipped a step, but if you did 1 over cosine x plus sine over cosine x, you get, so 1 over cosine x is the same thing as secant x, plus sine over cosine x is the same thing as tangent of x, and that's how you get that. So again, you want to look at the answer and see what it is. If it's separated, like with a plus or minus, that means at the end you're probably going to have to, or somewhere in here, you're going to have to separate this division into two terms. Somehow, someway you've got to, because that's what the answer says. If it's all multiplication, like this problem, then you're probably just going to want to end up with one division and then get the answer like that. Again, I found more practice helps you find out these things on your own. It's hard to explain, but I'd say doing the homework is very helpful. So if you didn't do the homework, then do the homework. Let's go on this problem. This one was a bit difficult. This took me some time as well. Let me get my thumb out of the frame. All right. So it's secant x minus tan x squared equals 1 minus sine x all over 1 plus sine x. So here we have a single division, as you can see. So what I did is we see our answer is given in sine and not just sine, right? Here they give us secant and tan. Now, see, again, there are tons of different ways you can go with this, but you're probably going to want to eventually turn these tans and secants into their respective cosines and sines. Just turn this all into cosines and sines because that's what the answer gives you, right? So you need to use the answer as a clue as to what you should be doing. So here it gives you in sines, here it gives you the answer in sine, something 1 minus sine x over 1 plus sine x. So you'd probably want to convert these into sines and cosines, right? So we get 1 minus cosine x minus sine x over cosine x, just using our basic reciprocal identities, there to convert that. Secant is the same thing as 1 over cosine x. Tangent is the same thing as sine x over cosine x, or sine over cosine. All of that squared. You cannot forget this is squared. That's still part of the problem. And then I just decided to combine the terms, because if you see cosine x is the same in both denominators, why not just combine the terms? That'll make our life easier. So we get 1 minus sine x over cosine x squared. Now, you can do a lot of things with this. Honestly, because this expression is the same thing as 1 minus sine x squared over cosine squared x. To deal with things like this, you just square the numerator and square the denominator. So if you see something like this with a square over the whole entire thing, you just square the numerator and square the denominator, and that's how you get the answer. But you have the option of leaving it like this, 1 minus sine x times 1 minus sine x, without actually combining the terms, or you could combine the terms. Now, initially I combined the terms, and that got me nowhere, so you're probably going to want to just leave it expanded. Because why? Because maybe, as you see later in the problem, you can cut things. That's why we like to leave things expanded in some scenarios. Again, going about from problem to problem can be quite difficult as to finding what you should do, but try every solution and try everything you can get. So we have 1 minus sine x times 1 minus sine x all over cosine squared x, right? Because numerator, denominator. Cosine squared x. Now, I see that, and I instantly look back to my Pythagorean identities, because I know I can convert cosine squared x into sines. And you know how our answer is in sine, right? This cosine seems out of place, all right? So now you'd want to use your logic, all right? If the answer is given in sines, wouldn't I want to convert this into a sine? Probably. That's what you're going to probably want to do. So if you look at your, again, Pythagorean identities, we use the first one. Cosine squared x is the same thing as 1 minus sine squared x. Now you're here, and it seems like you're really quite close to this answer if you look at it. 1 minus sine x times 1 minus sine x all over 1 minus sine squared x. It's looking kind of similar to this. It's getting there, right? But we still have the sine squared x, and you cannot cut anything, right? Now, you might get stuck, but if you remember, this is actually a dot. So this is a difference of 2 squares, which means you can expand that into what we eventually get here. So the numerator we keep the same, 1 minus sine x times 1 minus sine x. This denominator turns out, since 1 minus sine squared x, that's the same thing as 1 plus sine x times 1 minus sine x. Now we can cut things, and we can finally get our final answer. So we cut 1 minus sine x and the 1 minus sine x, and we get our final answer of whatever is left, which would be 1 minus sine x over 1 plus sine x. That's our answer. So in different scenarios, you might want to leave this as it is, or sometimes you might want to multiply it out. Again, you have to test it. Honestly, I was stuck on this problem for quite a while. But for things like this cosine squared x, you are going to want to use your logic to know that, oh, I should probably convert this into sines, so that way it leaves me in an answer that is sine, which is what we're looking for. All right, another problem. Secant x over cotangent x plus tan x equals sine x. All right, let's see. So the answer is not given in addition or anything like that. So we're definitely not going to end up with like secant. I mean, in this case, you couldn't even do this, but if we wouldn't want to do like something over something plus something over something, we're not going to want to do that, because that would separate our terms, and that's not what we're getting here. But then again, you can try whatever you want, see whatever works, just know your options, right? What I did here is I converted this secant into a cosine, because again, see, you have tan, cotangent, secant, but none of those are present in our answer. Our answer is given in sine, which means you're probably going to want to convert all of these into sines and cosines, which is what I do. So it's the same thing as 1 over cosine x divided by, I put this division symbol just because I didn't want to make it too complicated by putting another bar here. I just like to do that sometimes. There we go. Gotta fix that. Cotangent x is the same thing as cosine x over sine x. Tangent x is the same thing as sine x plus cosine x. So I did that, and we're going to need to add them, right? Now I can see an opportunity here to possibly use our Pythagorean identities, because sine x and cosine x, what if we combine the term? That would force us to multiply this, then that would result in squares, which means the possibility of using our Pythagorean identities and maybe getting an answer. So sine x, cosine x, we're going to make that the denominator, which means you're going to have to multiply this by cosine x and the numerator by cosine x. That gets us cosine squared x. Cosine x, to get this denominator, you're going to need to multiply by sine x. Sine x times sine x is sine squared x. Again, now we have these squares, so now we have options. We can do something with that, right? Cosine squared x plus sine squared x is 1. Nice. So now we can simplify that to just 1. Now we have 1 over, oh goodness, 1 over sine x times cosine x. All right. And now that this is simplified, because, you know, you could have done this all over the whole bar thing, but I just wanted to make this simpler. So now it's 1 over cosine x times, now you're going to want to flip that, right? Sine x times cosine x. The cosine x's will cut, and you get our answer of sine x. Again, these are the ways I did it. There are probably other ways of going about it that I haven't tested, but the main pointer is to, again, use that answer as a key and always try to use your Pythagorean identities. But use them wisely. Use them when you think they'll be helpful, right? You don't want to convert sine into like cosine when that's not even a part of your answer, right? You want to do something reasonable. All right, cosine x plus tan x times sine x equals secant x. Secant is a version of, secant is the same thing as 1 over cosine x, or secant x is the same thing as 1 over cosine x. Tan is probably a big thing in the way that you don't want to keep in your answer, because it's not in the answer. Tan cotangent's nowhere to be seen there. And besides, in most cases, I believe you're probably going to want to convert tan and cotangent into their respective sines and cosines, as well as secant and cosecant. You're going to want to turn them into sines and cosines, because you can always turn them back at the end of the answer anyway if you need to, right? This sine x over cosine x, let's say the answer had a tan x here, you can always convert this back into tan x and your answer will be there. Just for the sake of simplicity, you should probably turn your tans and cotangents, all of those, into sines and cosines. So that's what I did, right? I turned tan is the same thing as sine over cosine. Sine is just sine. So we're going to want to do the multiplication first, obviously, because of PEMDAS. You're not going to want to do this addition until you multiply these first. So we get cosine x plus sine squared x over cosine x. Now, see, I'm just thinking of this right now as I'm looking at this because it's been a day. You could technically convert this sine squared x into 1 minus cosine x if you wanted to, but I mean, I guess what I've done here is I just added them. And actually, think about it, it is more easier that way, more reasonable, because if you did do that, this cosine x you could imagine as cosine x over 1, right? If you do multiply this cosine x, if you do try to get a common denominator of cosine x, you'll end up with a cosine squared x up here, won't you? And since it's being added to the sine squared x, this gives us a opportunity to use an easier Pythagorean identity. As we know, cosine squared x plus sine squared x is the same thing as 1. So this just ends up with 1 over cosine x, which is the same thing as secant x. I bet if you converted the sine squared x into 1 minus cosine x, cosine squared x, you could probably get the answer, or maybe you would get stuck. But again, just know your options, try everything, always look at the answer, do things that are reasonable, and be sure to use those Pythagorean identities. Those will help you a lot.